Everyone, I am Saurabh Chauhan, and today I will be taking you through my research on what I call silent betrayal, the devastating impact of TOCTOU vulnerabilities on operating system security. These vulnerabilities are fascinating because they are like digital sleight of hand. They exploit the tiny gaps between when a system checks something and when it actually uses it. They are silent, they are stealthy, and they are surprisingly powerful. Let's dive in. What exactly did I investigate? I analyzed 137 CVEs and 42 real-world exploits across Windows, Linux, and Mac OS. That's a lot of security holes. What's especially interesting is how I developed a novel taxonomy to classify these attacks and discovered something pretty alarming. Modern architecture actually increases vulnerability surfaces by 37%. The question driving my research were how do these vulnerabilities manifest across different operating systems? What detection method actually works? And how do you balance security fixes with performance? Because let's face it, nobody wants their system grinding to a halt in the name of security. Let me break down how TOCTOU attacks actually work. See this gap right there? This is where all the magic happens. And by magic, I mean security nightmares. This system checks permissions, all good so far. But then there's this time window before the resources actually get used. That's where attackers strike. They swoop in during this gap, changes the resources, and by the time the system uses it, boom, the security check is now meaningless. What makes this attack so devious is that to the system, everything looks normal. The check passed, the resources were used, all logs show authorized access. It's like a perfect crime, except we are going to catch it. Doctor vulnerabilities are not new. They have been haunting us for decades. Bishop and Dilger firstly described them back in 1996, and Wei and Poo later identified a staggering 224 vulnerable systems called pairs in Unix system. More importantly, researchers like Xerxes and Goldwyn showed how this attack works in kernel memory, while others have explored them in containerized environment and cloud infrastructure. But here's the gap I found in the research. Despite all of this work, nobody has created a comprehensive framework that works across different operating systems. That's where my research comes in. My approach combined technical analysis and experimental validation, the best of the both worlds. I dug into CVE database from 2018 to 2023. The source was Mitra CVE database and analyzed open source code bases from Linux kernel 5.15, Windows NT, and Mac OS XNU source code, and interviewed 12 security professionals who live and breathe this stuff every day. What makes my approach unique is the 4-tier classification taxonomy I developed. This allowed me to map attack surfaces across 42 distinct vectors and analyze the temporal pattern of this race condition. I know, sounds like fun, right? Trust me, it was actually pretty exciting when patterns started emerging. Here's what my taxonomy revealed. TOCTOU vulnerabilities cluster into four main categories, with file system based attack leading the pack at 43%. These involve things like file access, symbolic links, and metadata manipulations. Memory management TOCTOU attacks account for 27%, followed by interprocess communication mechanism at 18% and process control at 12%. But here's the real interesting finding. 76% of high severity vulnerabilities involve multiple subsystems interacting. That's why they are so hard to detect with conventional tools. They cross boundaries that most security tools don't. When we look at the distribution across operating systems, Linux leads with 47 unique vulnerabilities, followed by Windows with 43 and Mac OS with 31. What's more particularly concerning is that 16 vulnerability patterns are shared across platforms, showing common weaknesses in fundamental design approaches. This data was taken from analysis of CVE database that was from 2018 to 2023. Breaking it down by severity, We found 18 critical vulnerabilities with CVSS score between 9 to 10. These are the ones that keep security professionals up to at night. The data was taken from CVSS scoring by NIST, National Vulnerability Database. The majority fall into the higher category with 53 vulnerabilities, while 42 are medium severity and 24 are low. But remember, even low severity vulnerability can be stepping stone to bigger attacks. Here's where things get really interesting. Modern architecture like microservice, which are all the rage now, actually increased TOCTOU vulnerabilities vector by 37%. Container orchestration introduced 22 unique attack patterns, and cloud-native developments expand the attack surface by 28%. Why is this happening? It's a perfect storm. Increased inter-process communication, complex privilege boundaries, resource sharing between containers, and distributed security enforcement. Essentially, the same feature that makes this architecture flexible and scalable also makes them more vulnerable. Irony, isn't it? So how do we catch these silent attackers? I test various detection approaches and the results were eye-openings. Traditional system call monitoring catches only 43% of attacks, with the frustrating 31 false positive rate. Static analysis tool do better at 57% and behavioral analysis reaches 68%. But the approach I developed, combining temporal pattern analysis with behavioral monitoring, achieved at least 87% detection rate and only 7% false positivity. That's a game changer. By analyzing the time pattern between operations, we can spot anomalies that other method misses entirely. Let me show you a real-world example. CVE 2021-3560, a critical vulnerability in Linux Polkit authentication system that went undetected for over 7 years. This vulnerability allowed complete system compromises that from an unprivileged user. The attacker exploited a race condition between dbus message processing and user ID verification. By canceling authentication requests at precisely the right moment, attacker could trick the system into granting admin privileges. What's particularly concerning is that this affected default configuration was remotely exploitable. Using my framework, we identified similar pattern in 11 other components that hadn't been flagged yet. Based on my finding, I developed a multi-layer protection framework with three key components. At kernel level, we implement transaction support for critical operation and research versioning for sensitive objects. The system call interface get enhanced parameter validation with temporal binding and operation atomicity enforcement. For developer, we provided static analysis pattern and API design guideline to prevent this vulnerability in the first place. The result, the approach reduced successful attack by 94% and 3.7% performance overhead. That's a security you can actually implement without user compliance. Of course, there were challenges. Comprehensive protection has performance impact, compatibility issue with existing application, and the external problem of false positive management. Our approach focused on selectively enforcement based on risk assessment. We developed a gratitude implementation strategy that focuses on high value target first, giving you the biggest security bang for your performance buck. This sweet spot here, 94% protection and 3.7 overhead, represents the optimal balance we found between security and performance. Looking ahead, I see several exciting directions for this research. We need to extend analyze to embed an IoT operating system, which have their own unique temporal challenges. Formal verification method could help create truly talk-to resistant interface. Machine learning approach show promise for adaptive detection that improves over time. And I am particularly excited about hardware assisted prevention mechanism that could eliminate this vulnerability at their sources. To wrap up, this research provides a comprehensive taxonomy of TOCTOU vulnerabilities, a novel detection methodology, and a practical mitigation framework with minimal performance impact. The key takeaway: time matters in security. By addressing the temporal dimension of security, we can close these silent gaps that attacker exploits, making our operating system fundamentally more secure. Thank you for your attention. I'm happy to answer any of the questions.